Purpose of this presentation is to kind of go over not so much the drive itself, but things relating to the drive that we may run into or may experience some issues with. And I was going to go typically I almost a 10,000 foot level view of this. This one we're going to go a little bit deeper into maybe why, what is cable charging current, and maybe what is it, what causes it, go a little bit deeper that way type of thing. So we'll talk about cable charging currents, maybe some of the cable construction and why we want to use shielded cable versus non-shielded, that type of thing. Look at reflected wave, over voltage issues, EMI, grounding is always a big one we're going to take a look at as well. And maybe a little bit deeper into the power source configurations and the jumpers. And then again, we always kind of wrap it up with the panel construction best practices type scenario. But kind of what I wanted to kind of start out with first was just kind of an overview of kind of what we're looking at type of thing here, right? So typically, and I'm going to kind of refer back to this kind of drawing or some of the components out of this drawing type of thing. So of course we have our comprised of a power source, AC drive, and the AC motor. There'll be all kinds of interconnecting cables, protective devices like fuses, circuit breakers, that type of thing that we want to be concerned with as well, and possibly input and output filters as well. And then if we kind of look at the drive itself, we're looking at the different components within the drive, the input filtering, and there we can see the PE, the famous jumpers that we'll talk about quite a bit as well. I'm going to be primarily talking today about the input rectifier just being a 6-pulse rectifier. We do have an active front end which uses a different topology or technology, but today I'm just going to focus just on the 6-pulse front end or 6-pulse technology. And we'll kind of look at the DC link, some of the issues in there, and again we find another jumper in there that we'll talk about as well. But this is another spot where we find the dynamic brake is in there as well. And then on the inverter we have the IGBTs that I'm not going to say cause issues, but are one of the reasons for some of the remedies that we'll talk about today. So I mean, for some basics, if we start looking at this and just kind of, I know a lot of us are on the line here kind of know this already, but sometimes it's good to kind of go over it again. But all electrical circuits consist of the power source and load. The power source produces voltage, load draws current from the power source. Current flows from the source through the load and back to the power source. If we don't have that, if there's a break in that connection, we don't get current flow. The product of the voltage and the current is the power the load absorbs, so it's the combination of the two. The important concept is that the current leaves the source, must complete the circuit and return back to the source, which is kind of always is an important one for us in this case. Another important thing is the ground that we'll kind of be emphasizing throughout this presentation. Ground is a conductor. Metal objects can be grounded, conductor wires can be grounded, electrical circuits are referenced to ground intentionally or unintentionally. Whether we like it or not, electricity becomes referenced to ground in one way or another. And again, we're going to kind of look at what that means to us. In an ideal power system, voltage and current are preferably sinusoidal with no harmonic distortion or noise signals. The current may not be in phase with the voltage, but that's okay because we have reactive, inductive, and capacitive components within the load source or the load side of the equation. Power source voltage and currents are always phase balanced, which we'll kind of find that's not always the case. And we're always going to assume that there's no current flowing in the ground or ground conductors as well in that perfect scenario, but unfortunately, we don't always live in the perfect world. So the next thing I was going to talk about is just kind of the AC drive inverter output characteristics. So what do we actually see? What is the drive actually doing here? So in this case, we're kind of looking at the output waveform of the PWM inverters as switched voltage, and the voltage that we're switching is off the DC bus. So the green trace in this plot is the output voltage, and it consists of a series of square waves pulsed with a fixed amplitude equal to plus and minus the DC bus voltage. So in the case of the common mode inverter, we aren't really, we're just switching the DC bus in this case. The width of the pulses varies to adjust the duty cycle and average output voltage. And then the pulse rate, or this pulse switching rate, or the carrier frequency, is usually about 1 to 4 kilohertz on the larger drives, and I know I've put up here 1 to 16 kilohertz on some of the lower power or smaller drives as well. Square waveform has infinite harmonics and will include frequency components in the megahertz range, because we often kind of get questioned as to where does this high frequency component come into play in some of the things that we're going to try to fix. The common mode noise, super high frequency, like well above a harmonic frequency, and that's kind of where it's coming from, is in the due to the PWM high frequency harmonics caused by that square notching in there. So and then all conductors have parasitic resistance, inductance, and most significantly capacitance between conductors and ground. So again, one of the other issues that we kind of have to deal with are the cables and the output of the drive to the motor, and how we're going to handle that too. So we'll kind of look at that a little bit closer. So at 60 hertz, the capacitive reactance is quite high and very little current results. So again, because we're having the high frequency output, that's where we get into all the issues, or all the things we have to deal with when we're just looking at something across the line, because we're going to talk about capacitance or cable coupling or cable charging current. We don't get that when we're running just at a 60 hertz sinusoidal waveform. So some of the other things we're going to look at, so current between conductors or differential mode, and current between conductors and ground or common mode current produces additional load on the inverters as well. So we're kind of talk a little bit about that as to why in some cases that sometimes we have to upsize the drive, and that kind of reverts back to this one here as well. So kind of the first thing I was going to kind of go over is that cabling. So, all PWM AC drives produce that square output, pulsed output. It's not just PowerFlex drives that do it, or Rockwell drives. It's kind of all drives that do it. We use the same kind of theory or technology behind it. There are three important effects produced by the high frequency current and voltage output of a PWM inverter. The first is the differential and common mode high frequency current, referred to as the cable charging current, that must be sourced by the AC drive. The red trace in the upper plot is the common mode current associated with the cable and motor line to ground capacitance. So if we kind of look at that, so if we kind of represent, what we've done there is put some inductors in there, as well as capacitors, and that's kind of representing the cable as it appears back to the drive. So what the cable is seeing, or what the drive is seeing, is that we have to do we have to charge that capacitance, and in doing so, we actually have to take some extra power from the drive, so we get that cable charging current affected. And secondly, the motor cable high frequency characteristic impedance is not matched to the motor impedance, so high frequency reflected waves are produced. So we get that reflected wave phenomena we keep talking about that we have to deal with, and the root cause of that is that our impedances aren't matched. So oftentimes we say, well, why don't we try to match those impedances, but it's not practical to do that. So we just kind of, it's easier to deal with the reflected wave than it is to try to get the impedances to match. And as a result of the cables getting longer and further away from the motor, that mismatch becomes greater. So if we can make the cables as short as possible, that phenomenon isn't as bad. And we can see 2 to 3 times DC bus voltage spiking down to that motor. So it's definitely something we need to take a look at and do that. So the reflected wave over voltage phenomena can produce corona arcing that can cause the motor and cable insulation failures. That's probably the most common thing that we usually have to deal with on a VFD installation. Is one of the more common things that everybody's kind of aware of. But there's another one in there. The third is the common mode currents, and if not properly routed back to the inverter DC bus link, we may find high impedance paths through various ground loops, creating common mode voltages. So again, one of the things we need to deal with is that common mode current, and if we don't deal with it properly, we get the EMI noise issues. So it's that high frequency component of the PWM that's coming back through the ground conductor through common mode currents and causing that high frequency to affect us. So if we kind of maybe take a look at each one of these individually, the cable charging current, what we're looking at there is the actual ringing effect of the actual cable, of the charging of the capacitance within the cable going out. One of the things I will say too is that typically this is an issue that we find in applications less than 5 horsepower. So the amount of cable charging current that's required is significant when compared to the motor FLA when we're under 5 horse. When we're over 5 horse, the drive usually has enough headroom or enough buffer in it that we can actually supply that enough of that cable charging current, and we can overcome that, and it's not an issue. But so it's on the smaller ones that we have to be aware of it. So how does it kind of expose itself, or what do we see when this becomes an issue? So one of the things we can see the worst is going to be the catastrophic IGBT failure. Over time, it won't necessarily be press the start button and it goes. It'll be something over time. So what we're doing is we're stressing the IGBT with high current requirements over a period of time, or we may actually trip out on overcurrent faults. We may also see drive ground faults as well. So again, just some of that may be induced back into the grounding of the drive. That extra current, that high frequency is induced because our grounding conductor is running in parallel with our 3-phase motor leads. We may get induced charging currents back onto the ground and may have a ground fault issue. But typically it comes back as a motor overload fault. And again, because we're kind of estimating the overload of the motor, because that extra current is going out, it is being consumed by the capacitance of the cable. The drive tends to think that we're overheating the motor. The motor is drawing a lot of current based upon the FLA of the motor that we put in. So we'll see that as well. The other one that we see quite often is this becomes an issue when we're using multiple motors on a low horsepower drive. So maybe on that 5 horsepower drive, we have 5 1 horsepower motors hanging off of it. And really at that point in time, the amount of cable is all of those 5 conductors going out all added together. So usually there's a fair bit of cable lead going, and the cable charging becomes an issue at that point in time as well too. So it is an issue that we find, but again, usually at the small horsepower. It's not really on the big stuff. The next thing I was going to look at as well is some of the mitigation that we can use around that cable charging current. Is well, first off, it's good grounding practices for motor cables, as well as using the characteristics that we specify in the installation manuals. Some of the other kind of things that we see oftentimes in the field is motor cables with twisted conductors. That'll cause more of the capacitance coupling, and we also see quite often 3 sets or more of motor cables in the same conduit. Again, small horsepowers, Contractors running a bunch of motors out to a specific area, and if oftentimes they'll run multi sets of motor leads in that conduit, then we get a lot of cross-talking going on there, a lot of cable capacitance coupling as well. So it's just, hey, we're saying, hey, no more than 3 sets in the same conduit, and we can kind of hopefully eliminate some of that capacitance coupling. Reduce cable lengths. That's a kind of a hard one to do. It's a physical requirement typically of the installation. But if we can keep the drive as close to the motor as possible, that's always a good thing. The other one is to the AC drive, the PWM carrier frequency. We can actually reduce that if possible to 2 kilohertz or less. I'm just going to kind of say again, this is kind of smaller drives, but on the bigger drives, the bigger guys are actually already reduced to 2 kilohertz. So the small drives, we typically default to 4 kilohertz as a carrier frequency. It's one of the things we can do there. The other one is to install a common mode choke in the inverter output, which is one way of putting some extra impedance into the line, short of adding an actual reactor or filter on the inverter output. But again, small drives, small horsepower, sometimes that gets a little bit costly to do that. Ultimately, usually what we get into is to oversize the drive. So again, if you had a 5 horsepower drive, we're getting cable charging currents, we may have to put in a 7.5 horsepower drive. We're just saying there not to exceed 2 times motor FLA. Just that's a function of the drive. Just that we have problems controlling the motor when we go 2 times bigger than the FLA of the motor. And then again, they're in the PowerFlex 750. We're starting to look at different algorithms in the firing of the power structure to reduce some of that cable charging current. But again, it's more of a phenomenon in the lower horsepowers, and usually we tend to not necessarily always use a PowerFlex 750 in a lower horsepower just because of the physical size of it. Next thing I was just going to kind of briefly talk about was just the motor cable characteristics. We have, and I'm going to refer to this quite often, recommendations in our drives -IN001 installation manual, and in there we specify what type of cables to use, and in this case we're using a shielded EMI shielded cable, but and there's the specifications down below, you can see there. It's a great recommendation. I mean, that's probably the ultimate installation. In reality, we probably run into more of the unshielded multi-conductor cables or separate conductors that we typically see in the field. And again, we do have some recommendations around that as well. What we see, I'm just going to maybe make some general comments around that. What we typically see in the past is sometimes we see some tech cable being used, and the steel conduit, they're assuming that's the grounding portion of it, but we like to see a separate ground conductor in that conduit, just so we can kind of get that grounding taken care of and eliminate it as best we can. Then the other phenomena that we have is the reflected wave, which is caused because of the high frequency surge impedance of the cable, and it doesn't match the motor surge impedance. Kind of was talking about that before. So again, hey, why don't we just try to match the impedances? Well, it's really not practical to match it, so we need to kind of deal with the issue. So voltage reflections, again, 2 to 3 times DC bus voltage at the motor terminals and within the motor windings. So what that plot that we're kind of have in the upper part of the screen there shows that without filters, in this case, this 10 horsepower motor has a 2 per unit reflected wave voltage with less than 100 feet of cable. The reflected wave voltage peaks at 2.4 units per unit at about 400 feet of cable. So it is highly dependent upon the length of cable that we have out there as to what the motor experiences as far as that reflected wave, and kind of how does this excuse me, expose itself. The big one is the corona causes the rapid insulation breakdown and failure typically of the motor. Usually the motor rewind guys, they can tell you because it's usually happens at the first turn in the motor windings. So they can usually tell you pretty quick that what has happened in there. Motor cable installation failure is the big one. The motor typically fails. And sometimes, in some cases, we've actually seen the actual cable supplying the motor, or the cable going into like the pecker head of the motor. It's starting to fail at that point. So even before the motor failed, the cable actually started to fail. So again, it's usually something happening out at the motor. The cables will fail close to the motor as well. The other thing we've seen as well is if they're on really old motors that did have a very high phase-to-phase insulation rating, they start to actually arc, and the arcing will actually cause failure of the drive. So the reflected wave punched through the insulation and actually caused some arcing within the motor itself, and that arcing actually ended up damaging the IGBTs within the motor, within the drive, excuse me. And the way we found that out, when we replaced the VFD after it had failed, the next one subsequently failed very quickly thereafter, and then we came up with that conclusion once we measured the motor. Then we found that was the problem. So. And again, measuring the motor, we found it very fast, as it failed very low. So I mean, we always get questioned on this is, when do I need to use, what do I need to do for my reflected wave mitigation, or what length of cable do I need to use? How far can I go without needing to use a reactor or anything like that? And really, it comes down to the motor itself, the corona inception voltage. And I've kind of put a little bit of a chart up there. And these are kind of the typical ratings that we see in the field: the 1,000 volt peak, the 1,200, 1488 is a very common one for the 480 volt. And then we see 1850 for the 600 volt applications. And really what that is meaning is that's the kind of the phase-to-phase insulation rating that it can withstand, from the reflected wave voltage coming out of the drive. And then what we need, once we know that, then at that point in time, we can determine how distance-wise, how far can we go from the VFD with that cable. So what I'm showing on the screen as well is in the bottom left-hand corner, there is a website, the web transom. We call it the transom website. It's a free website. You can go on there. You actually put very detailed information in there, even right down to the drive type, the voltage, the distance, horsepower, what the mitigation is, and down below in that screenshot, you can actually see the actual voltage and distance that we actually can predict that what will happen in your application. So it's a really good tool to use for that. But oftentimes customers will say, well, that's great if you know all that information, but usually I'm having to pick this before I actually have to do my installation. So what we've done is we've come up with, again, referencing back to that same publication, that drives-IN001. Within there, we actually will break down and give you a table as to the maximum distance based upon a scenario. So in this case, what we've done is we've shown, and at the very top up here, we're actually table 28, which is a PowerFlex 520 drive. In this case, it's a 480 volt drive. So if in this case, they picked a reactor only, and they've identified that their motor has a 1488 corona inception voltage, CIV. And if we kind of go across there, he's got a 5 horsepower application, which means he can go maximum or we would not recommend going more than 600 feet or 182 meters without going to the next level or the next step, which in this case would be reflected wave, or an RWR, a reactor and dampening resistor. But as you can see in this case, that there's no advantage of doing that. If we look at the 1488, I don't know if you can see my mouse there or not. If I take 1488 with the RWR, it's the same distance. So oftentimes it may not, the reactor is the best solution. Usually, again, this is a small horsepower drive. That's the case in the small horsepowers. A larger horsepower drive, usually we can get a fair bit greater distance with that reactor and dampening resistor. That's really it's really our version of a DVDT filter that you hear about in some of our Encompass partners that they sell and produce. Some of the other things we run into as well is EMI and grounding practices and different things like that. So we may have issues where customers are complaining that the drive is interacting with erratic operation of other issues. Actually, I'll pull them up here with other pieces of equipment, usually analog, anything analog, metal detectors. It tends to play havoc with as well. And typically, what it results in, or the way that we kind of can get rid of some of the nuisance ones, is just to properly ground the system. If things aren't properly grounded, we get a lot of EMI, radiation or noise pickup. It can also be unsafe as well if we're not grounded properly. Or we can do some mechanical damage to the bearings. So oftentimes if we have some induced currents in the rotor of the motor, high frequency, they'll try to tend to make themselves through the bearings of the motor. So that's why oftentimes when we have a VFD rated motor, the bearings are insulated to kind of help alleviate from that, because we can get some severe mechanical pitting of the bearings within the motor if we're not properly grounded. So what we're kind of showing here is kind of the way that we would like to see most systems properly grounded, and that being, one is the input transformer has a Y secondary, and with it being solidly grounded back down to in this case going back to building ground, and then we have a system ground, and that system ground is also brought back up to the drive itself, and that system ground is also back to the motor as well. As well as a ground conductor from motor to drive as well. So there's a lot of grounding going on in there, and good grounding practices do take a lot of these issues off the table. So again, kind of some of the mitigation practices that we see. Again, the power source with a Y connection and solidly grounded XO connection is a big one. We'll talk a little bit about what happens if we don't do that, but that's one. The shielded motor cables are another really a recommendation that we have, again, to get rid of some of the EMI or the radiated suppression, to suppress some of that. The common mode choke at the inverter output, we used to do that as a standard in our motor control centers. We don't do that anymore, but it's still an option there. And again, if we're having some of that radiated noise or interference with other devices, it is an effective way to kind of eliminate that, and it's probably the most cost-effective after the fact versus trying to replace motor cables and that type of thing. The choke is usually the least costly to do that. So the other one is, again, talking about motor bearings, it's difficult to add an insulated bearing after the fact. after the motor's been ordered and received. But again, I think today most motors that are VFD rated anyways will come with that insulated bearing. We do run across some shaft ground brushes, again, just to try to get that get those induced currents off of the rotor and back into a ground, and we just kind of pick them up off of the actual shaft itself with just a very, very simple brush. Usually we see that at the medium voltage level quite often, but like 200 horsepower and greater, we often see that too. So just some different scenarios to kind of clean that up. So some of the different grounding techniques that we have. So diagram just shows a complete AC drive circuit with shielded input cable, fused disconnect, line reactor, RWR filter or the DVDT filter, and a remote disconnect switch. So one of the things that we're trying to show here is just a contiguous ground connection right from the power source right to the motor. And in there we'll also have connections to the drive as well. So it's pretty critical that we have that in there. And we'll kind of look at each of these little bit closer. So these are the drive power filters. So PEA and PEB shown in the connected position for a solidly grounded power source. So I'm going to talk a little bit more about those jumpers as well, because it's pretty important that we do get them correct, and I'll show you what we do if we don't get them correct. So that's one of them. The other one we've kind of running across more and more frequently now is a local disconnect. So a remote motor disconnect. It's housed within its own steel enclosure near the motor. The enclosure is typically bonded to the plant ground, but the cable from the drive enters the box and another cable exits the box. But it's important to ensure that the cable ground conductor is continuous through the box and just not connected to the ground conductor on the box chassis. So sometimes what we see is let's say the drive to disconnect termination is to one side of the box, and the disconnect to motor cable is terminated to the far side of the box, and we're relying on the box being part of that grounding conductor in there. We've had some issues with poor ground connections and EMI radiation from that, and some different things. So what we're kind of saying is that we can kind of tie the two grounds together at some point in that box on a common little ground bus type of thing, or some way to kind of tie them directly together, not relying on the box as a conductor, is always a good practice. We're kind of finding that as well. What else we got here? And the just kind of in general, kind of all the good grounding practices all result in kind of a solidly grounded system that we typically don't see a whole lot of issues with. So oftentimes if we are having problems or some random nuisance things happening, the first thing we go in and look at is how is it grounded, and it's not just necessarily just at the drive itself, but we kind of want to see the whole system, right from motor right to power sources to how things have been how they've been done or installed type of thing. So this is kind of what we recommend as far as the power source goes anyways. We're always looking for a Y secondary solidly grounded to the system, and that being brought directly to the drive itself. So that ground as close as possible, as large a conductor as possible, back to that AC drive, back to the drive, so that we can get a solid ground in there. Some of the things that we're seeing more and more of in the field that we were able to deal with, but it just takes a little bit more consideration. One is the high resistance grounding. So we still have a Y secondary, but it's through a neutral grounding resistor or resistively grounded. And kind of the reason that the customers are doing this, or a reason that installation is there, is to limit arc flash potential. So just limit the amount of ground current that can flow back to the transformer, and we're going to limit the amount of arc potential that's available out there. But in doing so, what we're kind of wanting is that all grounds should be going through that neutral grounding resistor. But if we don't do some certain things in the field, we may have the ground, if there's a ground fault somewhere, go through the path of least resistance, which may now be the drive if we don't properly set our jumpers correctly. The other one that we're that we have some that we still see out there is the ungrounded or the floating system. This is not recommended. We do not like to do this. You know, the mediation around that would be to put an isolation transformer in, a 1-to-1. So put a delta Y 1-to-1 transformer on that, and be able to solidly ground the secondary of that so that the drive is happy that way. We see a lot of this in installations where we're doing conversions. So it might be an old DC drive system where they may have floated the system just because of the older DC motors would often go to ground quite often, so they would float the system so they don't have the ground issues on the motors. But when they convert them over to an AC system or upgrade the system, the transformers are often left in place, and then we have to deal with them then. So that's when we kind of get into that scenario, but we do not like to see that. We can get some high voltages present between the chassis of the drive and the internal power structure, and oftentimes we see flashovers and a lot of stress on the components in the DC bus for that application type of thing. So we just kind of don't like seeing that one. So this is kind of the kind of an overview of kind of the drive system here, and we're kind of, I don't know what we're going to show here. So the recommendations, in this case, I'm just kind of showing the 750-IN001. We also have the 520-UM001. Just kind of shows correct jumper connections. So we can kind of see the jumpers down in the bottom down here. I don't know if you can see my mouse or not, but I'm kind of circling where the jumpers are. We have a DC bus filter jumper, and we also have a common mode capacitor and an MOV or a MOV jumper down there as well. And you notice right now when it's connected, if there was a ground fault, what would actually happen, whether it be in our output of the drive or on some unrelated load that is off of the originating power source or the originating transformer, the ground fault will try to make its way back. If these jumpers are left in, will try to make it back through the drive and can cause catastrophic failure to the drive. It can cause nuisance tripping to the drive, and it can cause ground fault tripping of the drive as well. So lots of nasty things happening there. So what we're kind of showing is the in the installation manual, kind of what type of power source do we have and where do the jumpers need to be. So really, if we're solidly grounded in the system, that's what we like to have, is a solidly grounded system, the jumpers are interconnected. If we have anything other than that, we pull the jumpers or disconnect. So if you have an impedance or resistively grounded system or a floating system, pull the jumpers and do it that way. So that's true for all of the Rockwell drives that we have today. And just kind of saying what the jumpers are type of thing. So so one of the things that I'm just kind of showing here, what this is actually showing is we've got an example of kind of what the jumpers will do here. So these plots show high frequency common mode noise on the DC bus of a drive powered from a solidly grounded power source. So this is solidly grounded. No line-to-line ground faults are present in the system. So there's no faults on a good system. So the plot on the left is the PE jumper is removed, so it's disconnected, so it's improper. So the jumper is in the improper position on the left hand scope, and on the right hand scope we are properly, but you can see the amount of noise that's in there. This won't cause failure immediately, but what it does, it puts undue stress on the capacitors that are in the DC bus. So we power the drive up, pull it out of the box, put it in. We remove the jumper by accident, not supposed to do that, so it's improper. Power it up, and over time that drive will fail. And again, depending on how long it's going to take to fail, it depends on how hard the drive's working, that type of thing. So just kind of showing it, it's important to get the jumpers in the right position, and it should be something that you take heed of and write right into your operational procedures. I know oftentimes when we go in to do any service work to any drives, any PMs, one of the things that we do is always make sure the jumpers are in the right position, because it will over time can cause catastrophic failure. This one is just kind of an example. I'll go through real quick here, where we've got a resistively grounded distribution system. We have two drives on the same system. Drive number 1 is actually motoring, but he's actually got a ground fault. So there is a tiny residual ground fault on here. Drive number 2 is actually not even modulating, so he's not running. He's just powered up. He's just sitting there waiting to get his start command. And what we can actually see, what happens is, because the path of least resistance back to the transformer is back through drive number 2. So this ground fault is actually finding its way back through the power structure of drive number 2, and it's actually increasing the DC bus voltage on drive 2. It's not failing at this point in time, but it can cause undue stress and could possibly fail the drive. So there are some scenarios where things like that can happen, where jumpers may not be in the right position, and maybe that's what I didn't say. The jumpers are installed correctly on the DC common bus mode on this one. So just kind of some scenarios that we can run into if we don't have the jumpers in the right position. Some of the other things next thing I was gonna talk about is kind of the panel layout and construction of the panels. I'm sure we've seen messy panels, but maybe not quite this bad. But it's there are some nasty ones out there. What are the kind of the guidelines here? I think we all kind of know, hey, let's keep everything as separate as we can. The PLC stuff from the VFD stuff, and I think we're all pretty good on doing that, and that's usually pretty easy to do. It's not too bad, maintaining some specific distances between power and control wire trays and panduits, that type of thing. One of the other ones, though, is that we often see issues with is the distance between drive and panduit. In this case, we're showing a PowerFlex 750, if you can tell. Usually with the bigger drives, it's not an issue. We're looking for like 4 inches clearance. With a bigger drive, that's usually not an issue. It's the issues come into play when we have panel of a whole bunch of smaller drives. The PowerFlex 520s, they now need 2 inches above and below. And you think that doesn't sound like much, but we run into a lot of scenarios, a lot of installations where we don't have that clearance, and we're running into heating problems. And just because the panduit or the wire trays are slotted doesn't necessarily mean that we're getting proper ventilation. And we can kind of attest to that we do have a lot of customers that do put that panduit very, very close to the drive, don't allow for that 2 inches. of clearance, and we do have some heating problems and effects that come back to haunt us. So the other thing I was gonna kind of mention as well is the grounding. Again, kind of getting back to grounding, it's really important. And although we can always show it really nice and neat on an electrical wiring diagram, when it comes into practice, how it's actually installed in the field can often be sometimes a little bit different. So this is kind of what we like to see. We like to see, in this case, the outgoing motor cables kind of coming in the top. So those are the two left conductors or bundles coming in. You can see the ground is coming in and terminating directly onto the drive. From there, the drive is then brought down to a chassis ground bus. And attached to that chassis ground bus would be a copper bus, let's say, is actually the incoming power cables. Oftentimes what we see, well, we see a lot of different things, but one of the more common things that we see is the outgoing motor cable leads coming to a terminal block first, and kind of all the grounds being tied together there, and then a single ground conductor to each of the drives. We can run into problems doing it that way. We want to see each individual go back directly to the drive itself. The panel may look really neat by doing that, but we have run into issues by doing that. The other one that we see quite commonly as well is the motor cables are brought in and terminated to the, let's say, the mounting plate of the panel, and then the drive from the PE is just jumpered down to the mounting plate as well. So the mounting plate itself, the steel plate, is used as the ground conductor. Those are the ones we find a lot of issues with because it's now a huge, massive antenna. And either we're picking up a lot of noise or we're generating a lot of noise. It's just not a good scenario. So again, if we can kind of follow these as close as possible to get the motor lead as close as possible into the drive, as well as the incoming power cable, kind of a common chassis ground bus, and brought it back in, it'd be it makes life a lot easier, and very few issues when we do that. And again, kind of whoops, did I go the right way here? The cable distancing. Oops, I'm going the wrong way here. And this one as well is kind of the incoming actual box connectors. What are we using for that as well? Big thing here is when we see a lot of the tech stuff come in, just don't rely on the tech jacket as the only conductor when we're the only ground conductor when we're using for VFD installations is the big one there. So this was I'm just going to go through this a little quick. This was kind of a little bit more obscure type stuff that we have. For the nonlinear currents that we sometimes see, and in this case, usually the front end of our drives, our 6-pulse drives, are a diode-based system, and these rectifier devices, they're really a nonlinear load to the AC power source, and when it's a combination of nonlinear as well as distorted waveforms, repetitive high peak currents, and harmonic distortions, we kind of get that resultant waveform down on the bottom. And what does this really look like? It's really a combination of harmonics and unbalance of the system. What do we typically see? Tripping of overcurrent devices, fuses, circuit breakers. Input rectifier devices are failing as well, because we couldn't see massive spikes or big spikes on this. Harmonics are just not an easy thing to deal with, and usually if we have to deal with them after the fact, it's not inexpensive to do that. So if we can kind of maybe deal with them up front, and individually as we put our drives in one at a time type of thing versus having to deal with it as a system. It can be more cost effective, let's say. So just kind of giving you some information. This is just kind of some of the different harmonic content that we see, in the first column here. PowerFlex 520 with no line reactor, it can present up to 144% current harmonic distortion. So it's fairly high. Keep in mind, a 520 is relatively a small horsepower drive, so it's not going to really affect your distribution system that much. But when we maybe get up into a PowerFlex 750, we can easily, no line reactor, we can easily look at 38%. Now we can be, this can be starting to get into some bigger horsepowers. Now we can affect the distribution system a little bit more. But as we add line reactors into this, we clean that up quite a bit. So we're kind of just showing 38 down to 29%. I know we're all kind of used to hearing that IEEE 519, we want 5% at the point of common coupling, and that's at the point of segregation where Ontario Hydro comes into our facility. The 29% current harmonic distortion at the input terminals of a drive isn't huge, isn't that bad actually. So when we can go from a 38 to a 29 by adding a 5% line reactor, it's money well spent as far as issues with harmonics back onto the system, as well as being an isolation of let's say of issues from the distribution system, being spikes or noise or something coming in from there. I've also put on here too, and I said I wasn't going to talk about it, but I'll just mention it really briefly. The next generation of the 750 family is a 755 TL and TR, so it's their low harmonic and an active front end VFD. You can see these guys are dramatically lower harmonic content. Again, this would be at the terminal of the drive. Much lower than these guys. Again, more money, they're a more costly drive. No more diode front end, it's an IGBT front end. But just kind of showing you the differences between the harmonic content of those devices and what we can do by just adding a simple harmonic or by adding a reactor to the front to eliminate or reduce some of the harmonic content there. So some of the other things we can do is a passive or active harmonic filter, multi-phase input rectifier converters. So those would be like a 12 pulse or an 18 pulse VFD. Again, big bucks. You gotta pay for that up front and gotta know about it up front. You can't convert it in the field to one of these. And then the ultimate is the active front end or the AFE converter, kind of what these guys were over here, the TL or the TR that I was kind of talking about. But again, they're again, depending on how bad your harmonics are in your distribution system, a simple 750 with a reactor may be much more cost effective than going to a full active front end converter. So different things to think about and consider. So again, some transients. Again, kind of that's what the a reactor would help alleviate or reduce, let's say, is the rise time of some of these voltage spikes in here by adding extra impedance in there. Right. So again, where do we see it? Typically, when we realize that we have some high voltage spikes, we've probably cleared the front end of our drive, with either blown fuses on the front end, or we've actually blown the front end of the drive and we've had failure of the diode front end. So lots of things in there. And again, if we can just put that a line reactor or even ultimately an isolation transformer, like a 1-to-1 isolation transformer would be the ultimate. Zero crossing power factor correction, capacitor switching. I don't really implement that too often, but the reactor is by far the most cost effective to kind of deal with any of your known voltage spikes in your system scenario. So just kind of a summary of kind of everything that we've kind of gone over here. So kind of starting at the power source. So, looking at the transformer, if we can have that proper Y secondary solidly grounded is ultimately what we're looking for. The separate ground conductor coming into our VFD panel is ultimately what we're looking for. The line reactor, so that's kind of what the line reactor in there would be like. A line reactor, again, kind of cheap insurance that we were talking about there. Got to be aware of the jumpers, or kind of what our distribution system is, or our transformers with solidly grounded, resistively grounded, and what position our jumpers need to be in. As well as the output filter. Do we need a reactor? Do we need the DVDT or the RWR filter that we had out there? That's what the common mode choke would look like as well, again, for the EMI, to eliminate any irradiated type noise from our motor cables type of thing, and maybe even look at the motor cables as well for the continuous cable shielding, the local disconnect as well. How do we properly ground within that box? We typically kind of don't really think of it that often, but it's starting to kind of become an issue more and more that I'm finding. And then, of course, the motor itself properly grounded, and then the type of motor, is it is it VFD rated or not, type of thing. Some big things. So I was just going to put some of these things up as well, just some of the better reference material that we do have out there, that's readily available on the internet. So the drives, in 001, this is the one that I carry with me at all times. It has my cable length restriction tables, reflected wave distances, best practices grounding, wire and cable types. It's a really good installation, just general purpose type manual. The drives AT003 is more of an industry specific, so we cover off different industries, and here are the different industries: automotive, chemical, food and bev, forestry, marine, mining and steel, tire, and water wastewater. So very specific things that we find in those specific industries, kind of addresses that. And then we have a GMC RM001. This was actually developed by our drive systems team, and they just, hey, this is kind of the stuff that they would recommend that we do for each of these different things. So how do we properly install an encoder? What's best practice? Do we ground at both ends or one end, type of thing is always the big topic of discussion. Motor winding or motor wiring, power distribution. So it's just a really good, hey, here's how you do it. Here's the standards that we as Rockwell would follow if we were to do that installation. And then we have just the general installation manuals for the drives. So the 750 in 001, again, minimum clearances as far as that panel. How much space can I leave in there? Mounting considerations. Same with the 520 user manual mounting considerations. Again, more of an issue at the 520 drive, as far as distances between drives, as well as space between drive and panduit, that type of thing. And then I put in here the 755T. That's the active front end drive. Just some different considerations there as well. And then the last thing I was going to mention is, although this is kind of from 2018, it was it's called the Journal. It's a Rockwell Automation publication that you can find on the internet as well. It was that whole issue is kind of almost dedicated to VFDs, to power dissipation or distribution, as well as VFD cables, all kinds of really good stuff. So it's another really good piece of reference material that's out there on the web as well. So